In this video, I'd like to talk about the math question of the day for Sunday, April 23rd, 2023. And with this problem, we have an integral of a rational function here. And to answer a question like this, you will need the integration techniques that are typically taught in Calculus 2. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, we can start working through this. And if you do have suggestions for future questions of the day, feel free to leave those as comments. Now, a question like this type of integral can be a bit challenging, which is why in Calculus 2 we learn a variety of different techniques for various situations. Integrals, in general, tend to be fairly difficult, whereas derivatives are straightforward. Some of them can be challenging, but it is possible to find the derivative of any function because of the chain rule or the product or the quotient rule. Rules like that allow us to take derivatives of any known function. However, when finding antiderivatives, it's often not that straightforward. In fact, some functions, when finding their antiderivative, cannot be written as simple elementary functions, like polynomials, rational functions, trig functions, exponential functions. It's just not possible to express the antiderivative in one of those forms. But the nice thing about integrals is that there are still many different techniques that can be used. And since this is a rational function, for starters, we can try a substitution. We can say that u is equal to this denominator, then we write du as 2x plus 5 multiplied by dx, but you can hopefully see the problem here that we have no way to substitute du for dx since we don't have a linear term in this numerator. And even if we did have a linear term, it has to be a very specific one. So a substitution is not possible here, but because it's a rational function, we can try to rewrite this as a sum of other fractions. And we call this a partial fraction decomposition. So we can rewrite this integral here as a sum of two fractions in this case, though sometimes you can write it as a sum of multiple fractions. And there are many different rules to remember on how to do it properly, so it can be a little bit complicated. But once you learn the general technique, it is relatively straightforward. Now, to start this, what we can do is factor out the 4. And we would have 1 multiplied by dx, so I'll just write dx up top, divided by this quadratic. And you might notice that this quadratic expression can be factored. That's always worth checking, though often it doesn't work. We're looking for these two binomials. We know the first term in each has to be x, since x times x would give us x squared. And we know that these constant terms have to multiply to negative 14. And out of the factor pairs for negative 14, we need to find a pair that adds to positive 5. We can write out the list, minus 1 and 14, 1 and minus 14. We can do 2 and minus 7, or minus 2 and 7. And it looks like this pair here will actually add to positive 5. So we have x minus 2 and x plus 7. And of course, we can check this by just re-multiplying everything out. Now, at this point, we can rewrite this fraction here as a sum of two fractions. And to do that, let me first rewrite just our fraction here, 1 over x minus 2 multiplied by x plus 7. We want to rewrite it as a sum of two fractions where the denominator in each of these is one of these factors. We can have x minus 2 here and x plus 7 here. And think about this in reverse as if we are starting with a sum of two fractions, and we would need to find a common denominator. We'd multiply top and bottom of this fraction by x plus 7, top and bottom of this one by x minus 2, and when they recombine, they end up with this. But we would need to figure out what the numerators would have to be so that the numerator in our combined fraction would just be positive 1. And since we don't know what these numbers are, we can just call them A and B, or whatever letters you want. Though, if we don't have linear terms here, you do need to be careful. For instance, if this was some quadratic term, you would need to have a linear term in this numerator here. And that's one of those rules that you learn when looking at several different examples, but luckily for this case, this is one of the simpler ones where it's more straightforward. Now, to figure out what these constants are, A and B, we can manipulate this equation. We can multiply both sides of the equation by this denominator here, this x minus 2 multiplied by x plus 7. So that on the left-hand side, we just get 1. And on the right-hand side, when we distribute this denominator to the first term, the x minus 2's would cancel, and we would just have x plus 7 multiplied by a. And when we distribute this denominator to the second term, the x plus 7's would cancel out, and we would be left with x minus 2 multiplied by b. So we have plus b times by x minus 2. And from here, we can use some tricks to figure out what a and b have to be. For instance, if we set x is equal to positive 2, that would make this expression 0, and we would have an equation where we can just solve for a. So let's do that. We would still have 1 on the left. Then we have a multiplied by 2 plus 7, which is 9. Then we have b multiplied by 2 minus 2, which is 0. So we've simplified this to 1 is equal to 9a, and from there we can divide each side by 9 so that we get a is simply 1/9. And we'll do the same thing for this other expression. We can continue this trick. We can set x equal to -7 so that we get 1 on the left-hand side, but this first term here would just be 0 since we have -7 plus 7, and 0 times anything is 0. But over here we have -7 minus 2, which is -9, so that we get minus 9b, and solving for b, we would just get minus 1/9. So we've simplified everything so that we can find our constants here, a and b, which will help us decompose this fraction into a sum of two fractions. And let's write in what we found, that this is equal to a over x minus 2, but a is 1/9. So we have 1/9 over x minus 2 plus minus 1/9, so let's just make it negative 1/9 over x plus 7. And you can check your work by multiplying these back together. Again, we'll just multiply top and bottom of this fraction by x plus 7, and top and bottom of this fraction by x minus 2. And once everything simplifies, you will end up with this starting fraction. But the original purpose of all of this was to evaluate this integral. So let's rewrite this integral with a sum, or in this case, a difference of these two fractions, which is equivalent to this integrand here. We have 4 multiplied by the integral of 1/9 over x minus 2 minus 1/9 over x plus 7, and we have dx on the outside, and we will need to continue this integral. So let me take a picture and we can work on it down below. So let me make a little bit of space here so that we have room to work. I will paste in the picture of what we have so far. And to start, let's simplify everything. We can split this into two separate integrals, and we can factor out the 1/9 in each so that we get 4 over 9 multiplied by the integral of 1 over x minus 2, or dx over x minus 2. Then we're subtracting. When we factor out the negative 1/9 here, we have minus 4/9 multiplied by the integral of 1 over x plus 7, or dx over x plus 7. And these two integrals are now simple enough that we can solve them. You you might notice that each of these evaluate to a natural log. But if you don't see that, we can look at, let's say this one, where we have the integral of dx over x minus 2. We can use a u substitution. U is equal to that denominator of x minus 2. And du would just be 1 dx. So we can make a nice clean substitution. We have the integral of du over u now. And you might recognize that this integral evaluates to the natural log of the absolute value of u, which in this case, since u is x minus 2, this would just be the natural log of the absolute value of x minus 2. And it's an indefinite integral, so we would have an integration constant. Actually, we would have that here as well. So we can apply that to both of these. In this one, you would do the same thing, a u substitution of x plus 7. Du and dx would be equal, but we would end up with a natural log of the absolute value of x plus 7, all multiplied by this constant here. And let me actually do this down below here, so that we get 4/9 multiplied by the natural log of the absolute value of x minus 2 minus 4/9 the natural log of the absolute value of x plus 7, and we would need our integration constant from each of these, but in theory we can just add those constants together to get a new constant, which we can call c, or c1 if you want it to be different than this c here. So this right here should be our final answer, though as an exercise I encourage you to check this by differentiating this function here and seeing if you get back the original fraction that you started with.